Welcome to Lesson 9, Hypothesis Tests Concerning Means. Let's quickly review the steps of a hypothesis test that we looked at when we talked about hypothesis tests for proportions. So first of all, you need to make a claim. The claim should be in terms of an inequality, such as less than, greater than, or not equal to. And the claim concerns a parameter. Before we discussed the population parameter of the proportion, and now we're going to discuss the population parameter mean. The next step is to have your null hypothesis. Your null hypothesis is a statement of equality, so it will always contain an equals to. This value in the null hypothesis is the assumed parameter that will be used to find the probability value. The alternative hypothesis, H1, is the same as the claim. Once you've figured out your claim and formulated your null and alternative hypotheses, you want to choose a significance level, alpha. The significance level defines the unlikely probability, and you will use this and your p-value to determine whether the claim you made is supported or not supported by the data. What you're going to do once you've formulated your hypotheses and have chosen a significance level is make sure that you have the information you need to do the test. This includes sample statistics and the computation of a t-score when it comes to testing claims about means. The testing claims about means involves using a student's t-distribution to find the p-value, so you need to use a t-score, and the t-score is going to be computed using the sample statistics, the mean and the standard deviation and the sample size. Once you have your t-score, then you're going to find the p-value or the probability value. Remember, this is the probability of obtaining a value at least as extreme as the sample statistic you obtained. And by extreme, we mean either smaller or greater as defined by the tails. Once you have your p-value, you will compare it to alpha to determine your initial conclusion. And once you have your initial conclusion, you will then write a final conclusion, and the final conclusion will be written as a complete sentence. So let's review a few things here about the t-score. A t-score is found according to this formula, which says find the difference between the sample statistic, so that would be your x bar, and your assumed parameter. That's the value stated in the null hypothesis. You want to find the difference between those two values and then divide by the standard error. Now recall that the standard error, when you're working with one sample size and one mean, is the standard deviation of your sample set divided by the square root of the sample size. If you're working with a claim concerning two means, setting them equal to each other, the sample statistic will be the difference between these two means. So when you do the t-score, your sample statistic will be the difference between your two sample means. The assumed parameter will be 0, and the standard error is going to be computed using both standard deviations and sample sizes from your data sets. So the standard error when performing a test comparing two means is going to be the square root of the standard deviation from sample 1 squared divided by sample size 1 plus the standard deviation from sample 2 squared divided by the sample size 2. In order then, once you have those t-scores, you're going to find your p-value using the student's t-distribution. And if you're working with a left-tailed test or with Excel 2007, you will just use t-dist and tell it whether it's actually you just use t-dist, and if it's a one-tailed test, you have to use a positive t-score and tell it one tail. And if it's a two-tailed test, then you'll again use a positive t-score and say two tails. If you're working with Excel 2010 for a left-tailed test, you will use t-dist. For a right-tailed test, you will use t-dist right-tailed. And for a two-tailed test, you will use t-dist two-tailed. And to remind you about the rejection rule, if your p-value is less than alpha, you will reject the null hypothesis and support the claim. So remember that the smaller the p-value, the more strongly the claim is supported. Claims are only supported with small p-values. Otherwise, you reject your null hypothesis, and therefore you do not support your claim. So let's put all this into practice then, looking at some examples. So let's look at example 1 here, denoted as exercise 1. So here we have the weights. We are given the weights of a sample of 10 Canadian pennies and found out that the sample mean of these 10 pennies is 2.92802 grams, and the sample standard deviation of these 10 pennies is 0.36398 grams. We want to test the claim that the population mean weight of Canadian pennies is not equal to 3 grams. So notice the claim here is that the mean is not equal to 3 grams. So that's the population mean. I'm actually going to insert the symbol for the population mean, which is mu. So the claim is mu is not equal to, and I'm just going to use a not equal to for my symbols also. The claim is that the mean, population mean, is not equal to 3. So when we form the null hypothesis then, that's going to be that the population mean equals 3. So insert the mu for the population mean, and that will actually equal 3. Now we want the alternative hypothesis, H1, and recall H1 is the same thing as the claim, so I'm just going to copy and paste. Now we need to choose our alpha. Common alphas, remember, 0.05, 0.01 or smaller. Because I'm looking at the precision of these weights, you might want to use 0.01. However, the sample size is rather small. A sample size of 10, because it's a small sample size, we'll just go with the 0.05. Alright, so now it's time to look at our data and get our sample statistics. So notice the sample mean, x bar, is given to us as 2.92802 grams, and the sample standard deviation S, but I'll just call it standard deviation S, is given to us as 0.36398 grams. Now we are going to use this information to find the standard error. So recall that the standard error when working with one mean is the square root of the sample standard deviation. Oops, I made a mistake. Let's start over. The standard error is just the standard deviation divided by the square root of the sample size, which is 10. So here's our standard error. I'm going to use that standard error to compute the t-score. So recall that the t-score is found by taking the difference between the sample mean, okay, our sample statistic is the sample mean, minus the population parameter, the assumed parameter, which we are assuming is 3, and then we have to divide that by the standard error. So we get a t-score of a negative 0.62537. If you are working with Excel 2007, you're going to use a positive 0.62537 as your input when you find the p-value. So just to remind everyone, the sample statistic, okay, is the sample mean x bar. So when I computed the t-score, all right, we see then we're going to do sample statistic minus assumed parameter. So the sample statistic was the x bar minus the assumed parameter, which is always from the null hypothesis. That's why you have an equals in your null hypothesis statement, because we're assuming we're working with a distribution that has a mean of 3 in this case. And then we have to divide that by the standard error. So now that we have the t-score, we're ready to compute the p-value. So to compute a p-value for a test concerning a single mean, we are going to use the student's t-distribution, which is a statistical function, and it's t-dist. Now notice here, I need to do a two-tailed test because, and I'm going to go ahead and come back to that, we have to do a two-tailed test because the null hypothesis here is a not equals to. So remember, not equals to in the alternative, the alternative hypothesis is a not equals to. Not equals to means two tails, so we need a t dist 2t. So let's go back to t dist 2t. X here, that is your t-score. And the degrees of freedom is always one less than the sample size. We have a small sample of 10, so the degrees of freedom is one less than that, or 9. And we have an issue here. T dist 2t. What did it not like? X and degrees of freedom. Perhaps I need to also use a, let's see, maybe I need to also use a positive value. Let us then take the absolute value of this difference. So I can go to math trig absolute. So we want the absolute value of, and that will be the x bar minus the 3. And yep, that was it. Okay, so it looks like for a t-dist 2t, we also need to use a positive z-score. So that was good. All right. So we have a p-value of 0.547, right? So again, let's review the t-score. The t-score is going to have to be a positive value when using a two-tailed test. So we have the absolute value to make it positive of the difference between the sample mean and the assumed population mean. All right, so that's what the ABS is for absolute value, to make that difference positive. And then we divide it by the standard error to get the t-score, so that when we found our p-value, or the probability defined by the tails, we used our t-score and the degrees of freedom to get a p-value of 0.54. Now that is very large, right? That's like greater than 50%. That is obviously large. So for the initial conclusion, we see that the p-value is not smaller, right? The p-value is definitely not smaller than alpha, but greater. So the p-value is greater than alpha, so do not reject the null, do not support the claim. And the final conclusion is that the sample data do not support the claim that the population mean weight of Canadian pennies is, and this, I know you're not going to like this, all these quasi-negatives equal to 3 grams. So you might just want to say that sample data, if we just put it in simple words, it would look like the population mean weight of Canadian pennies could be 3 grams. That's basically what we've determined here. So as far as just saying, making a statement or a conclusion about what we've done here, it's a little easier to say the population mean weight of Canadian pennies could be 3 grams, right? We did not support the claim that it's different from 3 grams. Okay. All right, so that was one example. Let's look at another example. So here, exercise 2, we have another example, and this one refers to the volumes of 24 cans of Pepsi. We found that these a sample of 24 cans of Pepsi had a sample mean of 12.27 fluid ounces and a standard deviation of 0.09 fluid ounces. And we want to test the claim that the population mean volume of cans is greater than 12 fluid ounces. So our claim, okay, is that the population mean, which is denoted by the Greek symbol mu, is greater than 12 fluid ounces. So that means the null hypothesis, which is always equality, is that the population mean mu actually equals 12 fluid ounces. The alternative hypothesis is the claim. That's why we always state our claims as inequalities. And again, small sample size. Let's choose an alpha of 0.05. And now we can list our the information that was given to us. So we see that the sample mean, I'm just going to write that here. I'm just going to write it sample mean x bar, but I'm just going to write the sample mean, okay, is 12.27. The sample standard deviation is 0.09. We'll use this information to find the standard error. And remember, that will be the standard deviation divided by the square root of the sample size, which this time is 24. And now we can use this information to find the t-score. So recall that the t-score is going to be the absolute value of the difference between the sample mean, the assumed population mean, which is 12, and then we're going to divide that by the standard error. Hold on a second. I'm sitting here using the absolute value. We actually don't need to use the absolute value. Unless you're using Excel 2007, you don't need to use the absolute value in this case, because notice that H1 is a greater than. So this is a right-tailed test. We're going to be working with the right tail. And you probably already did notice that the t-score is actually positive, because if you're working with the right tail, your mean here, the sample mean, is greater than the assumed mean of 12. So I'm not going to worry about absolute values in this case. I need to divide that difference by the standard error. Wow, a t-score of 14.696. Okay, almost 15. The t-score is equivalent to a z-score in that it is the number of standard deviations away from the mean, assuming that our mean is 12 in this case, and that we're saying here that it's over 14 standard deviations away from the mean. That is extremely far away, so this is going to have an extremely small p-value. So the p-value, this is a right-tailed test, so when we go to our formulas, statistical, we're going to use a t-dist right-tailed. So t-dist right-tailed. We use the t-score as our input. So the t-score is a 14. The degrees of freedom, one less than the sample size. Our sample size 24, so our degrees of freedom is 23. Now notice this output here, this p-value. Right? The p-value is actually the most important part of doing any test. You see 1.7, but you remember p-values are probabilities, which can never be greater than 1. So this is not 1.7. If you actually look all the way to the end here, you see there's an E, which tells you this is in scientific notation. And that negative 13 actually means that this number is equivalent to the decimal, in which the decimal point here is moved 13 places to the left, which means you would have 12 leading zeros. So 0.13 12 zeros before you hit the 175. This is obviously a very tiny number. It is essentially 0. So when we do our initial conclusion, we can readily see that the p-value is definitely less than the significance level alpha. All right, very small. And in that case, we always reject the null hypothesis and support the claim. Because remember, the smaller the p-value, the more strongly the claim is supported. So the smaller the p-value, the more strongly the claim is supported. So claims are only supported with small p-values. Let's go ahead and make this big and bold, because this is very important, right? So the two things highlighted here are extremely important. We have a p-value, turns out to be essentially 0, and we know that the smaller the p-value, the more strongly the claim is supported. So a mean of 12.27, which is 0.27 fluid ounces greater than 12 fluid ounces, that 0.27 difference is extremely significant. Extremely significant. So the final conclusion then is that the sample data, and I'm actually going to add in here because I feel like saying it, strongly support the claim that the population mean volume of cans of Pepsi is greater than 12 fluid ounces. Obviously, PepsiCo is afraid of being sued if they do not give at least what they have stated on the can, so they have erred in the direction of too much in the can rather than too little. Right, so here was another example of a hypothesis test. This one turned out to be a right-tailed test for a single mean. Let's do another example. Let's look over here at exercise 3. Look at this data. This one we are given list price of a house and a selling price of a house. Notice I'm listing or labeling the list price like a before data value and the selling price as an after data value. The list and the selling price are dependent pieces of information because they both apply to the same house, the same home. So what we have here is a dependent data set. When we work with a dependent data set, even though it looks like we have two different samples, since they're dependent, we think of it as a single sample. And so the single sample we're going to work with are the differences. And the differences here are going to be the before minus the after. So we are working with the differences. So we want to do the before minus the after differences. So I am going to have a data set that consists of the before minus after differences. Notice that this data set's kind of all over the place, right? We got some positive values and some negatives, but it looks like we have a lot more positive than negative values. With the more positive values, that means the before was larger, which then it looks like the list prices tend to be larger than the selling prices. So notice the claim down here. We're going to test the claim that the population mean list price is greater than the population mean selling price. So when we look at that claim, okay, we're basically saying that the mean of the before, so the population mean mu of the before prices is greater than the population mean mu of the after or selling price. So mu before is greater than mu after. Notice this is equivalent to actually doing, if we rewrote this as a difference, I could write this as mu before minus the mu of after is greater than 0. Okay, so the claim that the before or list price is greater than the selling price is equivalent to the claim that the difference of the before minus after or list price minus selling prices is positive. It's greater than 0. Okay, so that is the claim. The null hypothesis then is going to be that the before minus the afters are equal. So let's go ahead, put that in here, but now I'm going to change this to an equal. If I do that, then an equivalent way of stating it would be that the difference between the two prices is positive, or I'm sorry, is equal to 0, right? So in the claim, we have the before greater than the after, or the list price greater than the selling price, which means that the list minus the selling, or before minus after, would be positive, greater than 0. The null hypothesis is a claim of equality, so it would be claiming that the before minus the before price and the after price, or the list and selling prices, are equal, which is the same thing as saying the difference between those actually equals 0. And then the alternative is simply the same thing as the claim. Alright, so there we go. We need to choose an alpha. Again, since I'm working with a small data set, I'm just going to choose an alpha of 0.05. And now we need the sample statistics. So our sample statistic will be the sample mean and standard deviation, sample standard error. So we know the sample statistic is going to be the average of these differences. So what we need to do here is, since we're given the data, we're going to do our data analysis and our descriptive statistics then to get these differences. So let's go to data, our data analysis, descriptive statistics, and this here, my input are my differences, and I'm going to click labels because I want it labeled differences, and I'm going to go ahead and put this on this page so we can see it. I'll just kind of, okay, let me fix that. So my input are my differences. I want my output range to be on the same page, so I'm just going to click that. Hopefully it'll put it in there. And we need our summary statistics. Okay, so here then are those differences. I wonder what happened to everything else here. I actually don't like, a little nervous about that. Okay, so let's see. Let's undo this. What happened? All right. Okay, exercise 3. Something funky happened. Well, here is the data put on a different page. So let's just look at this. And okie dokie. So let me grab all my stuff back here. So let's get this. So we can see I have the information over here on this other page. I'm going to just bring it back here since I kind of lost everything. Alright, so there's our data, there's our differences. And let's go ahead and review since I messed this up. We want to test the claim that the list price is, I'll just say here, significantly greater than the selling price. So when we did that, our claim could be written in 2 ways. We could do the mean of the before, which is list. Let's do a different time. The mean of the list is greater than the population mean of the selling, which is equivalent to the difference between these So that would be the difference between these being greater than 0. Because notice it was a right-tailed test. It's still going to stay a right-tailed test. Mu of the list price greater than mu of the selling is the same thing as mu of the list minus the mu of selling greater than 0. The null hypothesis will be similar, except with the null hypothesis we always put the equals to. So we'll have list price equals selling price, or the mean list equals the mean selling, or the mean list price minus the mean selling price. Whoops. Equals 0, and then the alternative is the same as the claim. Alright, we said to choose an alpha. We decided to choose an alpha of 0.05 because it was small. And then here is then where we needed our sample statistics. So I'm going to do that again. But this time I'm going to put it on a new page. So I don't know what happened last time when everything disappeared. So we'll do our data analysis, descriptive statistics. There are my differences. And my output range, I'm just going to put it in a new worksheet. And we'll just call it sum stats. And this is example 3. Okay, and here's our sum stats 3. Here are the differences. So notice then we have a mean difference. Okay, you can think of this as the mean difference, the average difference, a mean difference of 7 to 50. And here when we use our tool for the descriptive statistics, the standard error is given to us, so we don't actually have to compute the standard error from the standard deviation and the sample size. We'll just use the standard error. So we'll just say this is the standard error for the mean differences. So these are the values that we're going to want to use. So let's see if we can copy these. Take them back over here. All right. So there we go. Here's our mean and standard error. So this is what we're going to need. And the mean here, this is our sample statistic. So remember, when we are working with claims about means, we have to find a t-score. So the t-score is going to be the difference between well, actually, before I do that, notice that our claims all our claim and our alternative contain a greater than, so this is also a right-tailed test. That means our t-score is going to end up being positive. So equal the mean difference minus the assumed value from the null hypothesis. Notice that in our null hypothesis, we're claiming that the difference is 0. Here, the sample statistic and the parameter are both differences. So our mean difference is 7250. Our assumed difference is 0. Okay, so let us fix this. We need parentheses around here. And then we're going to divide that, remember, by the standard error. And here's our t-score of about 3.652. We don't need so many decimals. Let's just take this down. So there's our t-score. And remember, we're going to use the t-score now to find the p-value. And since this is a right-tailed test, we're going to do the t-dist right-tailed. So statistical functions, t-dist right-tailed, using our t-score for the x. Degrees of freedom, 1 less than the sample size. Oh, how many was that? That looks like it was, I guess, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1 less than 8 is 7. Wow. Okay. Now, because the big difference between 7250 and 0, so we ended up getting a p-value that is definitely smaller than our alpha. Okay. So in the initial conclusion, what we have here then is the p-value is less than alpha, so we're going to reject the null hypothesis and support the claim. So our final conclusion, the sample data support the claim that the list price is significantly greater than the selling price. Okay, and I really should say that the population mean list price is significantly greater than the population mean selling price. Okay, so the sample data support the claim that the population mean list price is significantly greater than the population mean selling price. All right, so that was example 3. Let's do another example. Okay, so let's look at, here's an example 4. Again, notice that we have this before and after data. So temperatures of healthy men, right? So these were body temperatures. So their temperature was taken at 8 a.m. Their temperature was again taken at midnight. This is dependent data because each temperature belongs to the same individual. We want to test the claim that the population mean body temperatures of healthy men are different between 8 a.m. and midnight. So this is another dependent test. So remember, even though you have what appears to be 2 different samples, they are dependent samples, so we can convert them into a single set of data by finding the differences between the 2. So the differences of the 8 a.m. minus the midnight. Want these differences. So we see some of these don't have any difference. Okay, and then we see there's several negatives, one positive. We have all negatives, one didn't change, one positive. So we want to know then, are these differences, these apparent differences, significant, or really it's just random sampling error? So is the population mean body temperatures of the before and after, are these things different or not? So the claim is they are different, because we always like to make our claim be an inequality. So the claim is that the mean before is not equal to the mean of after. So we'll say the mean of before is not equal to the mean of the after, which is equivalent then to saying that the difference between these is not equal to 0. So let's get that in here. So the mean before then minus the mean of the after is not equal to 0. Okay, so claim mean before not equal to the mean after. They are different. The null hypothesis, of course, is that they're the same. So we'll just take these here and we just need to change them to equals. So that's the difference between a claim and the null is always equality. So the null hypothesis is the claim that the before and after temperatures are the same, which means their differences are 0. And the alternative hypothesis is the exact same thing as the claim. So we'll just copy that. Okay. Again, I'm going to use an alpha of 0.05. When I have small data sets, I like to use 0.5. Bigger data sets, I will use 0.1. And we need our sample statistics. So let's go ahead then and have Excel do that for us. So let's go ahead with these differences. Data analysis, descriptive. Okay, and we want all of this in there. I have my labels, new worksheet. This will be some stats 4. Okay, and here it is. Remember, we only really care or need the mean and the standard error. So let's take these and bring them back to our problem. And these then are our summary statistics, or here we have our sample statistics. So again, we see the mean is negative, though very small, and you want to know, is that difference significant? And then we have the standard error. So this here, this sample, this is our sample statistic. Okay, that's the mean difference in the standard error. So remember then, when we're working with means, we need to find a t-score. So the t-score is going to be the difference between the mean and 0. And we divide that by the standard error. And we get a negative value. And we have a not equals to here, so we're doing a two-tailed test. And we saw earlier that with a two-tailed test, we actually need a positive t-score. So let's go ahead then, and we will take, let's do this. Let's just do, oops, okay, shoot. What did I do here? Let's undo. Okay, so is that it? So let's see, make sure I didn't screw anything up. So B18 minus 0 divided by B19, good. That's our t-score. Let's go ahead and do the absolute value of that. So that's positive, and we'll use the absolute value then to do our p-value, because we have to use the t-dist 2t because we have a two-tailed test. So the t-dist two-tailed, using our positive version. Degrees of freedom. All right, it looks like I have 9 data values here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 less than 9 is 8. Degrees of freedom, 1 less, 8. Well, look at that, p-value 0.045. Remember, I selected an alpha 0.05. So for this particular alpha, 0.045 is actually less. So that's interesting. So at the 0.05 significance level, we see that, actually let's do this, at the 0.05 significance level, we will reject the null and support the claim. What's interesting to note is, just kind of note, at the 0.01 significance level, we would not reject the null and not support the claim. So see how it matters what you picked. I deliberately picked a smaller significant, or this larger significance level of 0.05 because I had such a small data set. So with that small data set, my final conclusion does turn out to be that the sample data support the claim that the population mean body temperatures of healthy, and this was just men, are different at 8 a.m. and midnight. Okay, so that is our final conclusion. All right, so we've looked at 2 examples for one mean. We've looked at 2 samples for dependent means. Let's look now at some examples of independent data. So here we're given the volumes of cans of regular Coke and Pepsi. All right, so here we have larger sample sizes than before. With sample size is 36 for both, and we have means that are both around 12, but a little bit bigger, 12.19, 12.29, and then here are standard deviations. We're going to test the claim that the population mean volumes of Coke and Pepsi are significantly different. All right, we're going to test that they are significantly different. So again, we are doing a two-tailed test. Lots of two-tailed tests this go around. So the claim, okay, is that they're significantly different. We're working with two means. So again, let's say the mean, we'll say that the mean for Coke significantly different, so does not equal the mean for Pepsi. Okay, so the mean of Coke does not equal the mean for Pepsi, which is equivalent to saying that their difference does not equal 0. So let's write it in that equivalent way. Oh. But this time we want their difference does not equal 0. Okay, so this is the claim. The claim is that the differences, or the means, the population mean volumes are significantly different. So the mean for the Coke is not equal to the mean of the Pepsi, or likewise, the mean of the Coke minus the mean of the Pepsi is not 0. We know that the null hypothesis always statements of equality, so we're just going to copy these but change the not equals to equal to's, and that will give us the null hypothesis. And the alternative hypothesis, always the same as the original claim, so I can just copy that. All right. Alpha. Let's go ahead and do O5 again. All right, and now for the sample statistic. Okay, so our sample statistic, okay, is the differences between the means. Or the sample means. Okay, so the sample statistic is the differences between the sample means. All right, so that means, though, we'll just go in the order here, the mean for the Coke minus the mean for the Pepsi. Notice it's a negative here because the Coke was smaller. So our sample statistic then is a negative 0.1. Right? So the sample statistic is the differences between the means. That's a sample statistic. Now again, remember we do need a t-score, but to find a t-score we need to have a standard error. And if you recall, back here at the beginning, we saw that the standard error, all right, is found by taking the square root of the square of the standard deviation for the first sample divided by the first sample size plus the square of the standard deviation for the second sample divided by the second sample size. Right. So going back then to exercise 5, okay, let's delete that. This is going to be then the square root of the first standard deviation squared divided by the sample size plus the standard deviation squared divided by the second sample size, close parentheses. Okay, and here's our standard error. All right, so the square root of the first standard deviation squared divided by the sample size plus the second standard deviation squared divided by the second sample size. And now we're going to find the t-score. So the t-score, remember, is going to be the sample statistic minus the assumed parameter, which in the case when you're comparing two means, whether they're dependent or independent, is always 0. And then we'll divide that by the standard error. We see we have a negative number. We remember that, with two-tailed tests, we have to use a positive value. So we'll just do the absolute value of that t-score. And that's what we'll use when we find our p-value, which will require a t-dis 2t because it's two-tailed. Positive version, degrees of freedom, 1 less, aha. So here, 1 less than the smaller sample size. They happen to be the exact same, these two sample sizes, so it'll be 35. But you always want to go with the smaller of the degrees of freedom. So the smaller, 1 less than the smaller of the two sample sizes. All right, 1 less than the smaller of the two sample sizes. Oh, look at that p-value. That is small, all right? That is a small p-value. So the initial conclusion, okay, is that p-value less than alpha. That means reject the null and support the claim. Small p-value, support the claim. So the final conclusion is the sample data support the claim that the population mean volumes of Coke and Pepsi are different. All right, so there's our conclusion. All right, so this then was comparing to independent means. Independent means you still have the difference between them as your sample statistic, but the assumed parameter is 0, and you just remember here that the standard error was more complicated. All right, so let's look at one more example, and this will be another two independent means test. So we want to test a claim that the two samples come from populations with different mean weights. All right, so again, a naught equals 2. So different is very common, but don't forget we had a less than, you can do a greater than. Doesn't have to be just different. So let's go ahead then and test this one. So our claim is that, here we're looking at wheat pennies. Remember those old pennies with the little wheats on the back versus the Lincoln Memorial cents, which have Lincoln Memorial on the back. So, and they're both sample size of 35, so same sample size, so degrees of freedom will be 1 less, or 34. And let's see, so the claim is that the mean weights, population mean weights are different. So one more time, we're going to insert that the mean weight of, we'll just say, the wheat pennies, okay, is different, meaning not equal to the mean of the Lincoln cents. Okay, not equal to is the claim. Which is the same thing as saying that the difference between these is not equal to 0. Okay. Oop. Right. Okay, so the claim of different is that they're different means their difference is not equal to 0. So the null hypothesis is going to be that they are actually equal, or the difference is equal to 0. So all we have to do is change the not equals to equals. All right, and remember this then is going to be the assumed parameter is going to be 0, and then the alternative is the same as the claim. So we can just copy that again. alpha, I'll just do the 0.05. Okay, so now our sample statistic is the difference between the means, and so I'm doing the mean of the wheat pennies minus the mean of the Lincoln cents. Okay, oh, we got a positive difference here. We need the standard error. So remember, the standard error is the square root of the standard deviation, the first standard deviation squared, divided by the first sample size, plus the second standard deviation squared, divided by the second sample size. So there's a standard error. Now the t-score will be the difference between the sample statistic and this assumed parameter, which is 0, divided by the standard error. Okay, so there's our t-score that we're going to use to find the p-value. Once again, recall we are working with a two-tailed test, so that means we will be using the t-dist2t, and there's our t-score and degrees of freedom. One less in the smaller sample size. Both sample sizes are the same, so 34. Big p-value, 44%. Big p-value. So initial conclusion is p-value greater than alpha. Do not reject null and do not support claim. So the final conclusion is the sample data do not support the claim that let's see, the population mean weight of wheat pennies is different from the population mean weight of Lincoln cents. Alright, so the sample data do not support that claim that the population mean of wheat pennies is different from the population of wheat cents. Apparently the sample data support that the population mean of wheat pennies and Lincoln cents are the same. Okay, if you like that better. Sample data support that the population mean of wheat pennies and Lincoln cents are the same. Okay, so that was 6 examples. So I think that was lots of examples. We did a lot of two-tailed tests, but if you have a left-tailed, just use your regular t-dist. If you have a right-tailed, you can use the t-dist right tail. Okay, so I hope that helps. And that is the end of the presentation.